Good afternoon, guys. And today our topic is circuit theory and network theory. And you know that we are performing this lab through the virtual lab. You just open your virtual lab, VLab, and then you can find analog signal networks and measurement lab. Just click over this, then you can get this type of window. Just click over the list of experiment, then you can get this type of list. So today we will go for uh, first reciprocity theorem, then maximum power theorem. Okay, today we will go for maximum power transfer theorem first. Then we go for this Millman's theorem. You can see this is the Millman's theorem, because Millman's theorem, after doing this Norton theorem and Thevenin theorem, it is very much easier to you to perform this Millman's theorem. Okay, so first we go for the maximum power transfer theorem. Okay, you can see this is your theory portion. Objective, first your objective, verification of maximum power transfer theorem. The maximum power transfer theorem is transferred from a source of given voltage and an internal impedance to the load impedance ZJL in the following circuit showing in the figure 1 under three conditions. Okay, look, this is your circuit. So actually maximum power transfer theorem is saying that if your internal resistance is equal to the load resistance, then only maximum power will be transferred. Okay, this is the main objective. So you can see here is all about its equation and some resistance is there, formulas are there, you can perform it. Now we are directly going to the simulator. Just click on the simulator, then you can get this type of window. Then here, click here to perform this experiment. Just click over there, you can get this. Okay, so this is maximum power transfer theorem procedure. First, you should read this portion. If you don't read this, then you can't understand. Okay, first apply the supply voltage V in 230 volt and frequency is 50 hertz. Okay, this is just like your board uh, experiment kit. You can see this is the 230 volt and 50 hertz, so we no need to change it. Okay, and choose whether to connect whether the concern or the bypass the LS and the CS by clicking on the corresponding white checkbox. Okay, just checkbox. Yes, this is done. Look, this is LS and this is CS. Okay, means CS means source capacitor and LS means source inductor. Okay, uh, checkbox. By default, they are all connected. Tick sign indicate the components is bypassed. Now set the value of the different element of source impedance ZS when switch on the circuit board to get the voltmeter reading. Okay, just read again. Now set the value of the different element of source impedance ZS and then switch on the circuit to get the voltmeter reading. Just you have to set. So just you can abruptly set just one. This is 5. This is also very less. Yes, this is okay. You can get this. Case 1. Only XL is adjustable. Choose whether, look, if you power on, these are the bypass. Yes, this is 000. Okay. So case 1, only XL is adjustable. Choose whether to connect or bypass LL and CL, adjust them and click on the simulator to set XS equal to X minus XL. Check if, means this is the impedance portion in the source and impedance portion in the load. Okay. So check if the power transfer to the load PL is maximum, then check the corresponding efficiency. Okay. So this is case 1. Just simulate. We have right. Just put, this is 1, 1. This is 5. This is, we have given, this is okay. So if I simulate it, just put, okay. So power is 9.0016. Okay, x xs is 000, xl is 000, and the power is 9.0016 watt. You can see, and efficiency is, look, this is efficiency is 50%. Okay, if I change this, you can see this efficiency will be decreased or changed, not decreased or increased, it will be changed, and your power will be also changed. Just do this. For the case 2, only RL is adjustable. Okay, for the case 2, you can see only RL is adjustable, and click on the simulator RA and RL, where RA is root under RA square plus XS plus XL whole square. Check if the power transfer to the load PL is maximum and check the corresponding efficiency. Look, only we can adjust this. Okay, we don't do this. Okay, just simulate. You can see, as this RA and RL not same, then the efficiency will under 50%. But in the previous cases, the efficiency with same circuit, but efficiency was 50%. So again, we have to make it. We have to adjust this so that 1.9, it should be 1.9. Yes. Now you can see this is R is 1.9 for the RS, and this is RL, this is 1.9. Now if I check this efficiency, simulate again, you can see this is the 50%. The efficiency is 50%. Okay. If I mismatch this portion, say RA, this R source resistance and the load resistance is varying. Look, 1.9, here 1.9, but if I change this just 2.5, just change this, our source resistance is 1.9, but the load resistance is 2.05. So this is not same, this is a mismatch. And if you apply this Millman's theorem, sorry, maximum power transfer theorem, now you can see the efficiency is not under 50%, it will be decreased. Look, yes, or sorry, this is increased. So in this way we can change the efficiency, and load is 4.7308. Again we are performing this, just load is varying. Look, this is 4.56, or I am going to the abruptly, this is 5. Okay, then again simulate it. Yes, the efficiency is 72.464. Okay, now for the case 3, both XL and X are adjustable. Choose whether no connect, whether to connect or the bypass uh, XL or XC, adjust RL and XL, and click simulate to set RS equal to RL. Okay, and XL equal to minus of XL. Check if the power transfer to the load PL is maximum and check the corresponding efficiency. Look, just of this bypass one, only RL is adjustable. Sorry, here both XL and RL are adjustable. Choose whether to connect or bypass LL and CL. Look, first we bypass this LL. Okay, then X3. Okay, simulate. You can see your efficiency is 72.464. Okay, now again we bypass XC. You can see your efficiency is 72.464 again, but the what is decreased. Sorry, not decreased, that is changed. Whatever, I don't know the previous one, we don't notate it. So by this way we can examine where the maximum power is transferred. First one, we have just changed this load resistance and source resistance. Then we can change only the load inductor or only the load capacitor. Then we can see which one is the maximum power is transferred. So in this way we can find in which impedance we have to adjust so that the maximum power will be transferred. So again, if we start from this case one, you can see first when the efficiency is 50%, and just note down this wattage. Look, first, that is all should be same and no one will be bypassed. Look, this is the resistance, this is 1.9, this is the source resistance. Just I increase up to the 5. Look, this is 5. Okay, so now we have to examine what is the watt. Just click on this. Okay, just simulate. You can see the wattage is 1.8003 watt. So just write down it. The first case, your wattage is 1.8003. The case 1, guys, you can write down this case 1, that is only RS and R load all are all components, means resistance, inductance, capacitance for the source side, and the resistance, inductance, capacitance for the load side, all are equal. You can see all are equal value. Source resistance 5, load resistance also 5, source inductance is 0.0005, so load inductance is also 0.00005. Source capacitor is 0.00014, and the load capacitor is 0.00014. So all are same. Then we have to check the efficiency. Efficiency is 50%, and its the wattage is 1.803 watt. Now, if we just change the load resistance only load resistance, you can see, just switch off it and then you can change it. It will be changed, say, just double. Just we make it double. Look, this is 5, this is 10. Source resistance is 5 and load resistance is 10. Now, if we check this, just simulate. Look, your power is your power is 1.6003 and efficiency is till now 66%, but max power is not transferred, that is 1.6003. Means in previous cases, the power was as 1.803 watt, but now it is decreased up to 1.6003. So from this maximum power transfer theorem, you can see if we increase this, then the power will be decreased. If you increase the resistance, then power will be decreased. You can see this is source resistance is 5, load resistance is 10, and others are same. It may be same, or you may just bypass it. If you bypass it, just bypass it, just bypass it, just bypass it, just bypass it. Okay. Okay, you can see the simulate it. You can simulate. Look, XS, XL, or all are not here. You can see what wattage is very less, going to very less. Okay, in previous cases it was 1. So if we just check this maximum power transfer theorem on only resistance, then we can find, if I resistance increase this, say this is 100 ohm, this is 100 ohm, and this is also 100 ohm. You can see again, you can see what happened. You can see this is 50%, because 50% power consumed by here, 50% power consumed by here. Now if I make it double, just multiplied it by double, just simulate it, you can see the wattage was just double. You can just note down, in only applicable for the R. The wattage is 0.00017379. Okay, whenever only this resistance is working. But if I make it double, means that is 100 to the 200. Now load resistance, so maximum power should be transferred to here. You can see, yes, you can see this is wattage is just 0.0003467,675. Okay, but efficiency is increased because efficiency is increased because these are drawing in much of power. Means if resistance is multiplied with 2, then power also multiplied by 2. Okay. So now we are going for the one by one checking. First we have to check this XLS, means source inductance, and we have to apply source inductance, load rate inductance also. Look, here only we are applying this load resistance are same, means resistance are same. Look, RS is 100 and RL is 100 also. But we are first going to vary the inductance. Now source inductance is 0, this is 0.000005, and here is also 0.000005, same. And look, this capacitor is just bypass. For case 1 we are applying this. You can see, just simulate it. You can see same things are available, 17.379. Okay, and here also this we are applying just double. You can see if I make it double, just here is 5, we are applying this is 10, then we can see what happens. Look, in this case, though I make it double, sorry, yes, but you can see the if the wattage is same. Okay, by for the inductance there is no such change. Again, if we go for the capacitor value, look, it was 10, so you make it 5 again. Okay, now here is capacitor is there and we are bypassing this inductor. Okay, look, this is 14, this is 14, inductor or bypass for both case, load resistance, source and the load. Now if we check it, we can check it. This is wattage is 0.090016. First case only C is changing, that is 0.90016 watt. Efficiency is 50%. Now if I just make it double, this is 14, this is 14, but we are making 28. Just make it double. Look, if we simulate it, you can see wattage is not changing. Wattage is not changing. Though we changing this capacitor value. Look, in this capacitor, load capacitor, that is 0.00028. In this source capacitor, that is 0.00014. So not changing. Okay. Now we are applying this for both L and C. In this case, what happens? Just make it 14. Just make it 14. Now if we make it change, look, this is 0.9006 watt, 0.9006 watt. If I just make it double one by one, look, here is 5, we have to make this is 10, 110, here is 14, this is make it 28. Look, nothing is changing. Okay, for this is case 1, we can understand that if I only change the resistance, then only the wattage will be changed, means it will draw the maximum power. Now in the case 2, only RL is adjustable. So we have seen that if I change this RL, then only maximum power will be transferred over here. Okay, so click on the simulator RA, and RA equal to RL, where RA is the x square, RS square, RS plus XL, sorry, X S plus XL whole square on total under root. Check if the power transfer load PL is maximum and check the corresponding efficiency. Okay, so RA equal to RL, RA equal to RL. Check it. You have to make this change. Look, RA equal to 100 and RA equal to 100. Then you can see the what maximum power is here, and efficiency is 50%. Efficiency is 50%.
Hello, sir.
Yes, yes, tell me.
So, what is the objective of this experiment, sir? What we are finding?
Yes, we are finding in which point the maximum power should be transferred. Okay, just I am giving you an example. Say in your auditorium, your room, home theater, or your auditorium, you can see there is a 8, 10, 8, 16. This type of boxes are there, but there is a music. One device is there that is called sound mixer. You can add 4 boxes, you can add 8 boxes, you can add 8 into 2, that is 16 boxes in this way. But you have to adjust this load such a way that your this type of RA and RL should be equal. Means the load resistance and the source resistance, means load impedance and source impedance should be equal, so that maximum power will be transferred. Okay, if you add 8, if you add 8 boxes, then load resistance or load impedance should be defined, because in this speaker, I am saying about box, means that is a speaker. In this speaker, you can see there is a coil is there, there is some circuit is there where you can apply some capacitor, and ultimately it has some resistance. But actually what we want to need, we need this RA should be RL, so that your maximum power will be transferred. Otherwise you can see some speaker will not produce maximum sound. Some speaker are yielding very high sound, and some speaker are not giving you uh, much amount of sound, but you are connected in same sound mixture, same way. Why it is happened? Because it is happened due to your load is not matching, your maximum power is not transferred. This is the uh, practical experience which I have seen. But here you can see I want to show you I want to show you so many way that when your maximum power will be transferred. Look, whenever we apply just this resistance changing, then only your power will be transferred. Means your wattage will be changed. But whenever we change this capacitor or inductor, one by one I have performed here. If we apply this inductor or capacitor over there, if I make it double, then no impact was founded on this watt. Okay, there was same things was happened, same wattage was drawn. Same wattage drawn means same, a speaker, a device drawing some power, means it is giving you some output, and this output is showing by your watt meter. Okay, how much amount of output it is it is providing, you can find out by your watt meter only. Okay, means a speaker is giving you some sound. If you don't apply your uh, uh, audio meter, then you can find only by your watt meter. Some speaker drawing 10 watt, some speaker drawing 20 watt, some speaker drawing your 30 watt. So is that same? They are providing output, is that same? No. Which one giving you drawing 10 watt, if the others components are okay, then it means they are giving you some uh, decibel sound. If another speaker is drawing 20 watt, means it is providing some much louder sound. If another speaker is drawing 30 watt, it means it is providing you much louder sound. But in your auditorium, your theater, your home, just like your cinema hall, you can see there is so many speakers are there, are surrounding your area. And due to the length of this wire, the resistance is not same. Is their resistance are same? Whenever a speaker using one meter wire, whenever a speaker is using connected with a 2 meter wire, whether a speaker is connected with the 4 meter wire, is their resistance is same? No. But then, but we are want we we are demanding that all speakers should be giving a same sound, so that your auditorium seems to just like a Dolby sound, etc., etc. So in these cases, we can apply this maximum power transfer theory. Okay, so through this experiment, we are finding which resistance should be applied over the load, so that the maximum power should be drawn. The load, if the load drawn the maximum power, then we can understand uh, uh, the load giving you the maximum output. Otherwise, it will not giving you the maximum output. Okay, so is that clear?
So what will be the efficiency at maximum power?
If we go for 100% efficiency, not possible. Okay, but it is giving you 50%, means your internal load also draw some amount of wattage, and your another load resistance or load also draw the 50%. That's why it is giving 50%. So this is shown as a internal. Actually, if you give look, this is one speaker and this is one speaker. Okay, this is speaker one. It has some resistance, it has some inductance, it has some capacitance. Say this is speaker two. This is a resistance L, resistance inductance L, inductance C. If it is 50%, means 50% is load, 50% wattage is consumed by this speaker and 50% is consumed by this speaker. But you can see, if I just change this, make it resistance is 200, say make it 200, and now if you apply this, uh, you have to go case one. Sorry, it is not giving. Yes, it is case one. Now if you apply this, if you simulate, you can see the efficiency is increased. Now it is increased 66%. In previous cases it was 50%, but wattage became downwards. Okay, wattage means this load resistance will getting high, consuming high wattage, but this is not taking high wattage. So this, if it is a speaker, then this speaker will this sound will be quite lower than this speaker. Okay, so we have to make just like this 50% capacity. This is 50% means load are distributed, means wattage are distributed in both cases. 50% over here, 50% over here. But if I mismatch it, means there is some speaker is drawing much load, and some speaker not able to draw such type of load. So it is going to downward. It is going to damped. So this is the maximum power transfer theorem. We have to just look in this experiment. There is no table is there, no table is there, because this is for only for your realization, not for your tabulation format. Okay, but another experiment, others experiment has the some tabular format, so that you can realize this from this table. But here you can only experience the real thing from this wattage and efficiency. You have to check only the wattage and efficiency, in which point we are getting the maximum power. Okay, now if we apply this 2, then you can see, if I simulate it, you have to close this. Okay, look, this is RA is 100 and RL is 200. Okay, RA is 100, and look, this is the efficiency is 66%. Okay, now if I again increase or change this, just change this. If I change this portion, then this load will drawing maximum power, and this load is drawing maximum power means this load will give you the maximum output. If here it is treated as source, but if you imagine that it is another speaker also connected, then you can see this internal or this speaker will not giving you the sound is a maximum rate. It will dump. So what will be the your purpose? If you go for this distribution purpose, then you have to distribute equal sense. If you want to distribute this load maximum power, then you have to increase or adjust this, so that your maximum efficiency will come in. Now this is in this rate, you can see 66% means the distribution 66% wattage is consumed by this load, and another that is 34% of this wattage will be consumed by over here. If I increase more and more, if you increase more and more, sorry, if increase, just increase this, you can see 100% load will be 100% wattage will be consumed by this load. Look, sorry, you have to simulate. No, this is 66%. It is going to 66%. And if you go for over here, here you can see we have to check. This is again 66%. If I change this, so this is just change, make it 4. Just make it 4. Simulate it. Look, there is 80%. 80% efficiency means your load is consuming 80%, but your internal load, this internal load is consuming 100 minus this 80.117, that is that may become 20, around 19 point something. So it will be damped. So in this way, we have to adjust. Our load should be getting maximum power. So this is the main objective of maximum power. But in practical cases, somewhere you have to